we recall you what was the problem, at which point we are. So this is the problem. You have a functional. This functional is the functional associated to a focusing on linear Schrödinger equation made of a kinetic part and of a nonlinear part with the subcritical power p between 2 and 6. And this is a standard function on a non-standard domain, which is a graph. Okay? A non-compact graph. Non-compact means that this graph contains at least one half. Okay? Okay, this was the presentation, and let me get to the point where we arrived yesterday. So yesterday we saw that there are graphs for which there is a minimizer and graphs for which there is no minimizer. Okay? And in particular, I want to stress a point. When I say that there is no ground state, this may sound weird to some quantum mechanical ear, because in quantum mechanics, ground state it is very important. This is a sort of axiom, if you want. In 1913, Bohr made these atom models in order to avoid the problem of the collapse of the atom by radiation. Okay. And the axiom of Bohr's atom was, the first axiom was that there was a ground state. It was a level of energy below which it was impossible to go. So the existence of ground state is very important in quantum mechanics. But here we are not really in standard quantum mechanics, because here we are in a sort of non-linear approximation of quantum mechanics. So mean field theory. I thought about mean field theory in the first lecture. Moreover, the sort of non-existence of ground state I have here, it is not of the type of the collapse of the atom. So collapse of the atom, no ground state can have two aspects, basically. So the fact that the infimum of the energy is equal to minus infinity. Okay? This was the problem of the collapse of the atom. And this is the problem of other quantum mechanical models, which are known like Thomas effect. Okay? What is Thomas effect? This is a phenomenon that appears when you have a Hamiltonian whose spectrum is not lower bounded. So this Hamiltonian displays an infinite number of eigenvalues that accumulates to minus infinity. This is typical of the three-body problems in the case of delta interaction, for example, dimension 2 and 3. But this is not the case of our lack of ground state. Then there is another possibility of the lack of ground state, the fact that the infimum of E is finite. And in particular, yesterday, in many cases it was minus mu cubed over 96, where mu is the mass constant. But the point is that this infimum is not attained. So there is some sequence of functions whose energy tends to this limit, but this limit is not attained by any function. So this is the kind of lack of ground state that we are examining here. Tomorrow we will see other cases. So yesterday we ended by introducing the idea of rearrangement. And the idea of rearrangement is quite simple from a philosophical point of view. So take a function and replace it with another function. Construct another function that makes better, whose energy is less. And the recipe to do that, it's quite complicated from a mathematical point of view. So this is the definition of the distribution function. Okay, it is slightly different from the one I introduced yesterday because there is a sum of the edges. Okay, yesterday I just said that there is x in G such that the u of x is greater than t. Here I'm just saying take edge by edge and then perform the sum of the Lebesgue measure of any edge, but it is the same. So to any function u there is associated a distribution function. Okay, that measures the upper level of some level t. So the LP norm, the nonlinear term in the energy, can be computed by the distribution function. This is the form, sort of layer cake representation. So The nonlinear term depends only on the distribution function. This is the first point we stressed yesterday. And the second point, which is very important, is that if you consider two functions having the same distribution function, even though they are defined on very different domains, and then we define a function u hat on R, so it is different, R in general is different from G, or u star on R plus, and again it is different from G. So even though the two functions live in two separated worlds, then if they have the same distribution function, they have the same nonlinear term of the energy. And more importantly, what happens to the kinetic energy when rearranging? The kinetic energy of a function u is estimated in such a way in terms of the distribution function, so here is the first derivative of the distribution function, and of the number of free images of any element of its range. So this n of t is the number of free images of t. Okay. So the message here is that in order to make the kinetic energy decrease, then it is important to lower the number of free images. The more are the free images, the more are the oscillation, and the larger is the kinetic energy. So when defining rearrangement, it will be important to let this energy decrease, so to diminish the number of free images. This was the point yesterday. And yesterday we introduced a first monotone rearrangement, which goes from the graph to the half line. So this is the formula, but so that generically u star can be understood as being the inverse of the distribution function. And so we have, sorry, there is a mistake with the power. P must be here and Q must be correct. But we have that the u star has the same nonlinear part of the energy as the original u, but it has less kinetic energy because the number of free images of the u star is 1 for any. So you cannot be better than that. Okay. So that for any u, it is possible to construct a u star on R plus such that its energy is less than the energy of u. So in this sense, the best possible graph is R plus. Okay? Second, there is another rearrangement that goes from the graph to the line, and it is a symmetric rearrangement. Its rigorous definition is written here, but you can understand it in this way. If you have this row, I already displayed this picture yesterday, then you have u star, which is the inverse of rho, and then you can just squeeze by a factor to u star and extend it by symmetry, and this is u hat, the symmetric rearrangement. Again, distribution function does not change, so the nonlinear energy has the same value, but the kinetic energy decreases only, decreases only in the case that the original function provided at least 2 free images for almost every element of the range. Okay? Again, the estimate of yesterday, the energy of u under this hypothesis is greater than the energy of u hat defined on the line, but since the soliton is the minimizer on the line, the energy of u hat must be greater or equal to the energy of the soliton, and for example, for p equal to 4, this energy is equal to minus mu cube over length distance. So this is the starting point of yesterday. There are questions on this part. Of course, the theory, the rigorous theory of the arrangement is very delicate. Okay, a good reference is the classical book by Evans and Garay. Strange title like Fine Structure of Functions. It's a very beautiful book. very subtle from the mathematical point. But this is what we have to know about the arrangements in order to understand the following argument. So, first, we observe that if we have a graph G, non-compact graph G, and consider a function u in H1 with the mass constraint mu, so this is sort of mu symbol, this is H1, and for a reason of brevity, I just put mu here. This is our function in H1 with mass mu. Moreover, if almost every element of the range has at least two pre-images, okay, then the energy of U is greater than the energy of the soliton of the same. This is the main point. This situation, as I told you yesterday, is not exotic. Okay? It's not strange. Already on the line, it happens like that. Any function, H1 function of the line, has to go to 0 at minus infinity and at plus infinity. So every value in the range is attained at least 2 times. So this is the situation on the line. So the idea is the following. If the graph is made in such a way that morally every point lies on a line, then we are done. So what does it mean? What does every point lies on a line mean? It means that every point, from every point, you can go to infinity into different directions. Then the graph is quite complicated and so on. But if the graph is made in such a way that from every point you have 2 directions to go to infinity, so towards two different points at infinity, then as we will see, you are obliged to have at least 2 pre-images for every element of the range, and then this estimate still holds. Okay, this is the way. Now we realize the idea in an assumption, and the assumption in the language of graph theory, but very simple element of the language of graph theory, is the following. We suppose that every point of the graph lies on a trail. Okay, we'll explain you what is a trail. A trail that connects to different vertices at infinity. This is the hypothesis. So this is the graph. A trail is nothing but a line in the graph. So in a trail is made of adjacent edges, and vertices can be repeated, for example here, but edges cannot be repeated. This is the idea. So this hypothesis tells us that the graph is made a sort of bunch of lines. It's made of several lines, not disjointed. For example, our bridges of yesterday fulfill this hypothesis. Remember the horrible 2 bridge, which is very difficult, as I told you yesterday. So it is not possible to understand whether a minimizer exists by elementary considerations. So the idea is that you have 2 points at infinity, and every point lies on a trail that connects these 2 points at infinity. Okay? All possible trails are not disjoint, but this is not important. For example, if we consider this x here, then a possible trail is this one. It is not unique. You also can do. Okay. But for any point, there is one trail. And I want to stress that this hypothesis is topological. The length of the edges here do not count. They are not present in the hypothesis. So this is a topological hypothesis that ensures that any function has at least 2 pre-images for any point in the range. This is why. So in this way of telling the story, this seems to be very natural. Indeed, in the first paper on graphs, the big effort was to find out this hypothesis. And this hypothesis was found out in another version, which is a bit more complicated and so on. But then now, in some sense, cancelling all the technical stuff, the hypothesis remains there. my opinion is very clear. It's very natural. So, here again, here I introduce the notation of the theory is the following. Suppose that the graph G satisfies the assumption H. Then, the infimum of the energy at mass mu is equal to the energy of the soliton with the same mass. So, minus mu cube over 96 if P is equal to 4. But the point is that the infimum is never attained. So there is no final state. This is the situation. Okay. The infimum is finite, it's not minus infinity, but it is not attained. Except in some special cases that we call the bubble towers. This is a bubble tower. Okay. So bubble tower is a line, and then possibly there is a circle at a point, and then in the half point of the circle there is another circle, possibly larger or smaller, it is not important, and so on. Okay. All circles are cut into halves. This method is important. Halves in sense of. So here there is a minimizer, and we will see which is the minimizer. But in all other cases where the hypothesis H is fulfilled, there is no minimizer, and the infimum is given by the solenoid. So remember yesterday the example that we made yesterday of S3, 3 half lines, a star graph made of 3 half lines. And remember that we performed a simple but precise, exact computation on particular states made of 1½ soliton. What we found was that the infimum was asymptotically attained for sort of almost solitons running towards infinity. They were not exact solitons because here there is a vertex, and then here what remains here of the soliton has to be divided in 2 half-lines. It's not an exact soliton, so, and this fact makes its energy to increase a bit. But the point was that the infimum was the one given by the soliton on the line, and it was attained only asymptotically at infinity. And here it is the same phenomenon that happens. The infimum is attained when there is an almost soliton running towards it. So, I've sketched the proof, but at this point the proof is somewhat clear. Consider a function u on the graph, and of course this function has a global maximum point. It's a positive function. Remember that we are restricting to non-negative function, goes to 0 at all points at infinity. It must have a global maximum point. Let us call it x0. If G fulfills the H hypothesis, then there must be a trail T passing through H0 and joining 2 different points at infinity. And since x0 is contained in the trail, the maximum on the trail is equal to the maximum on the graph. Of course, it's u of x0. Now, T connects 2 vertices at infinity. x0 belongs to T. So, for almost every T in the range of u, the number of pre-images of u is greater or equal to the number of pre-images of the function u restricted on T, because T is a subset of G. And this number, the second number, is greater or equal than 2, because on the single trail, the function must start from the maximum of u on G and go to infinity in 2 different directions. Sorry, go to 0 to different directions. So every T has at least 2 pre-images already on the trail, so a fortiori it has at least 2 pre-images on the graph. And this tells us that the energy of u is greater or equal to the energy of the soliton. Sorry, in general it is strictly greater greater to the energy of the soliton because the soliton is the unique minimizer modulo translation on the tray, on the line. And the point is that the energy of the soliton remains the infimum because it is asymptotically obtained. And I want to stress that this hypothesis so prevents the existence of minimizers for every mass. A topological hypothesis works for every mass. It is a sort of duality between mass and length in this scheme. So for every mass, if the hypothesis H is fulfilled, there is no ground state. In this sense, that the infimum is attained by running away solitons, and it is not attained by any function. Okay. But of course, there are bubble towers, and now let me tell you why for bubble towers. Notice that the bubble tower fulfills hypothesis H. Okay? For any point there is a tray passing by this point, through that point, and connecting the two infinities. But what we can do in this case is just cut soliton in pieces and glue it on the bubble tower. It is quite simple, and I explained it by various symbols, but let me do it slowly at the whiteboard. So here is the soliton, and here you have your bubble tower. So you have these two circles. The first circle has a length L1, and the second circle here has a length L2. Okay. This is the soliton of the required mass, and first one can cut the soliton at a height such that the width is equal to L1, is equal to the length of the upper bubble. Okay, and okay, I call this part U. Second, one can cut the soliton at another height such that this part here, so from the previous cut to the new cut, is L2 halves, and here too, L2 halves. And there are two arcs isolated by the two cuts, and I call both of them V. Okay, so basically we have a function U, which is the head of the soliton, a function V, and so the support of U is L1, function V, which is given by these two intermediate parts of the soliton, and the support is L2. Okay. And I call the remaining parts W, W, and W. Now I simply take this U and put it here to the head of the bubble tower. This is the picture becomes quite ridiculous. Then I take this V and put it one here, one half here, and the other half here. And then on the line, so here there is part of the V with the other part of the V. Here there are the two W's, the two tails, on what is left. This is the construction. And in doing that, there is no change of energy. Okay, the function is the same. The analytical expression of the function is the same. Basically, this is a sort of topological line. It's a line with just some identified points. So it is not very surprising that you can mount a soliton. Of course, you cannot mount every function on the line here because there is this identification. Okay? Only if you put a 0 here, you can mount here only function that whose values are equal to, at point L1 over 2 and L1 plus L2. For example, you can mount every symmetric function. Okay, so these are the only examples where the hypothesis H is fulfilled, but where there is a ground state. The ground state is exactly the solidum. The energy of this guy equals the energy of the runaway solidum. From the point of view of calculus of variation, this is quite important examples where there are minimizing sequences that are vanishing and other minimizing sequences that are not. In any case, for our point of view, this is the only example where there is hypothesis H and a ground state. And now, so the question is what happens if hypothesis H does not hold? Is it a necessary and sufficient condition to guarantee non-existence? This is the question. Let me answer quite slowly to this question. The first theorem here is an unexistent theorem, and it says the following. Take a non-compact graph, and then in order to establish the existence of a ground state, it is sufficient to find a function u whose energy is better or equal to the energy of the solid. Okay? If there is a function whose energy is equal or less than the energy of the solidum, then there is a ground state. This looks quite easy. Try any function if you find it. Up to when you find a function which is better or equal to a solid. But okay, let me comment on this again. Remember, I'm saying that for non-compact graph, there is always this sequence of solitons, of almost solitons going towards infinity. There is always this. The sequence is a good competitor in some sense. Okay, it gives this value minus a near cube over 96 in the cubic case. Now, this theorem tells us that in order to have a ground state, it is sufficient to be better than that sequence. So that sequence, in some sense, is the enemy of the ground state. That is something going towards infinity. What this guy is saying is that the compact part of the graph, in order to produce a ground state, must be able to produce a function, produce a state, which is better than the solid, better than the runaway solid. So there is a competition from localized state and runaway solid. I don't show you the proof because, again, the technique is by concentration compactness theory. So I decided not to insist on that. Okay. But in any case, we can use this theorem and hypothesis H in order to, this theorem and the arrangement theory, but on intervals, in order to prove that for quite a large class of graphs, there is a ground state. So, when I say rearrangement theory on intervals, the point is that there is no need of non-compactness or no need of graphs or lines in order to define the arrangement. Okay. The arrangement can be defined exactly in the same way on interval. If you have an interval of length L and a strange function on it, then by rearrangement you can find a monotone rearrangement that goes from the same minimum up to the same maximum. It's a monotone rearrangement, or also a symmetric rearrangement on the same interval of length L. Okay? So it is possible to rearrange functions on interval without changing them. And of course, when we perform a monotone rearrangement of a non-monotone function, the energy strictly lowers, okay? Strictly diminishes. First example, this guy here that we call signpost. Okay, this is quite easy to see why there exists a ground state. We start from the from the two bubble tower. Remember how it was made? It was there were two. Okay, the length of the bubbles can be chosen arbitrarily. And here we had U, here we had half of V, the other half, and here W and W. This second bubble is of length L2, and suppose that we chose L2 exactly equal to the length of the pole of the sign. Okay. Now what we do is simply take this V, remember that V was made like that, and rearrange it monotonically. So we find something like that. That's a monotonic, sorry, it is easy. Okay. This is a monotone rearrangement on an interval of length L2. Doing this rearrangement, the kinetic energy diminishes as well as the energy. Okay? So, we take this function, rearrange it like that, and place it here. And place it here on the pole. Connections are good because minimum and maximum are expected. But the energy now is less than the energy of the minimizer on the bubble tower, which was exactly the energy of the solidon. So the energy of the function that we constructed is strictly less than the energy of the solidon. By the existent theorem, the ground state exists. Just using the arrangements. Okay. Notice that when doing this, it is not guaranteed that what we find is a minimizer. Indeed, in general, it is guaranteed that it is not the minimizer. But I want to explain why. The problem is condition on at vertices. Connections, after doing that, connections are continuous but are not good from another point. So it is not a minimizer. But it is not important. The important fact is that its energy is less than the energy of the source. So here we have a ground state which is better than the source. Notice also another thing, that here hypothesis H is not fulfilled, because if I take a point here, there is no train passing from this point and connecting the two infinities. If I start from here, in order to get this point, I have to go on the pole, but then to go to infinity I have to come back. And when coming back I run through the pole 2 times. This is forbidden by the definition. So here hypothesis H is not fulfilled, and indeed there is a ground state which is better than the solid. The second, the line with a pendant, this is very simple. Just start from the pole and without rearranging anything, just open the sign post. Again, there is no change in energy with respect to the sign post, so the energy of the state we construct is less than the energy of the solid. So there is a ground state. Third example, the so-called tadpole. The tadpole is quite easy, because you start this time from the sign post. You start from this guy. Here on the two half lines there was the same function w, the state we constructed, and now we rearrange monotonically together the two w's, and again the energy increases. Okay. So by the way, the tadpole has been extensively studied by Nonlinear, Perinowski, and Riccardo, and so on, because it gives some particular structure of a bound state with many bifurcations and so on. And again, there is a ground state. Last example is a bit more complicated. This 3-fork. Okay. It's a fork with 3 pendants and so on. And here we start by, this guy, the bubble tower. First, we rearrange W, the two W's, and get this W star, and the energy is better. And then simply open the the bubbles at the right point respect to the length of the form. And here we get a state which is better than the solitons, so a ground state exists. This is no longer true if we have a fourth pendant here. In this case, we don't know whether a ground state exists correctly. If you want, it is an open problem. In all these examples, notice that the ground state exists for every value of the mass. In this sense, they are topological. We did not make any restriction on the length of the arcs. For any length of the arc, it is possible to choose the length of the bubbles here in order to fulfill the requirement. That's not very good. So these are topological results. But topology is not always sufficient. Okay? Now we go to this example. When we take S3, so 3 half-lines, but attach a terminal edge or pendant, okay, of length L. So remember that without this terminal edge, there is no ground state. This is S here. Without one half line, this is the line with a pendant. It was the second example we discussed, and there is always a ground state. So the question is that what happens in a structure like that? So the result is the following. If L fixed mu, it is very important to fix mu. Fixed mu, if L is large enough, okay, this critical length L star is a function of mu. If L is large enough, then there is a ground state. If L is not large enough, there is no ground state. Okay? This is a so-called threshold phenomenon, or if you want, this is a mechanism which is present in some models of symmetry breaking, but here there is no symmetry breaking. This is just a break. I won't prove this, I will just discuss some points. First point is the following, in order to understand what happens. So, if you fix mu, then in some sense you fix a length scale, because the soliton of mass mu has a fixed length, which in the cubic case goes like the inverse of it. So you have a length scale. Now, if L is long enough, then you are able to place almost the half soliton of mass mu on the pendant. You put a half soliton here of mass mu. The half soliton is much better than the soliton, because it's minus mu cube over 24. So if you have almost half soliton here, you have a very low energy. Of course, it is not exactly a half soliton, because here there is some error, here there is some connection to be matched. But in any case, this error can be made smaller and smaller as L grows. So at some point you are able to do better than the soliton, so a ground state exists if L is larger. This is the first observation. The second observation is a bit more technical, and if L is short enough, then there is no ground state. This is an interesting point, but I cannot explain it in detail. The point is the following. Start from the 3 half-lines graph, what we call S3. This guy has no ground state. So, it is possible to prove that a small perturbation of this graph cannot produce a ground state. If you have no ground state, just by a small perturbation you cannot gain a ground state. This is the main point. So, if you add very small pendant here, you will not gain a ground state. But if you add a long pendant here, you have a ground state. So there are transitions from existence to non-existence. At least one transition as L grows from, sorry, it is the contrary, from non-existence to existence, okay, as L grows. And it is possible to see that there is exactly one transition. So there is exactly one L star for which below L star there is no ground state and beyond L star there is a ground state. And before sketching this more thorough analysis, let me just stress that this example is not topological, it's metric. Here L is important. Of course, for any value of L, H hypothesis is not fulfilled here. Because when you have a pendant, points of the pendant do not belong to any train connecting to points of the train. So H is not fulfilled. But in any case, there is no ground state if the pendant is not long enough. Here, metric is important. And let me show you why there is only one transition from non-existence to existence. Okay? You have some experiment on perspective here. So we have these three half lines, okay? 1, 2, and 3. They are black. And here there is a ground state of mass mu. Okay? This, because of perspective, here seems that at the vertex here there is no maximum, but in reality the maximum is here at the vertex. Okay? So this is a ground state. So L is already long enough. Now, this is called GL. Now consider the graph GL L prime with L prime greater than L. So what can we do? We consider on any half line a small interval of length L prime minus L over 3. So 3 intervals starting from the unit vertex. One interval for any half line of this width. Of course, putting together the 3 intervals, we obtain a length which is exactly L prime minus L. Okay. So the first thing we do, we consider the 3 pieces of this function corresponding to the interval 0, L prime minus L over 3. So there are three pieces which are equal because this state is symmetric. They are made in this way. 1, 2, and 3. Okay? And they live on intervals of this length. So 3 times this sort of intervals. And what we do is rearrange them together monotonically and obtain a single monotone function that lives on an interval of length L prime minus L. Again, there is a loss of pre-images because here, when you have 3 functions like that, any point on the range has 3 pre-images. When you rearrange them monotonically, you get 1 pre-images. So the kinetic energy we get is strictly less than the original kinetic energy. And then we put all pieces together. Now the picture is not beautiful like before, but the point is that here, from 0 and L prime minus L on the new pendant, which is longer, which is of length L1, we put this rearranged function. By rearrangement, the minimum and the maximum are preserved. There is no problem in junction, so the junction here is good, it's continuous. What if we have at the end that this energy, the energy of this function, is strictly less than the energy of the original function? Now, since that original function U was already a ground state, its energy was less than the energy of the solenoid. The energy of this new function is less than the energy of u, so it is less than the energy of the solenoid again. So it is, so there exists a ground state. So what one can prove by this simple application of rearrangements is that if for some L there is a ground state, then for any larger L there is a ground state too. So there can be only one transition from non-existence. So this is the first example of the influence of matrix. Okay? We are in the case where hypothesis H does not work. This means that non-existence is not guaranteed. When hypothesis H does not work, matrix can be important. This is the first example, but now there is another example in which hypothesis H does not work. Example is of this type. There is only one half line, and then sort of compact core of the graph. If you have only half line, of course, hypothesis H cannot be verified, because hypothesis H tells that there exists a trail that connects 2 points at infinity, at least one trail. But if you have only 1 point at infinity, there is no trail. Okay? So hypothesis H is not satisfied. But on the other hand, you can say, okay, but one half line is the best possible graph. How is it possible that attaching something here, you lose the ground state? Indeed, the first conjecture on which we worked was if you have only one half line, then you always have a ground state. But then we saw that it is not true. And this is the basic theorem, the basic estimate, which is the following. Given a graph G, there exists a number, a pure number epsilon, such that, okay, for P, for a nonlinearity P, there is this coefficient beta defined like that, such that, fix the mass, if this quantity, the mass to the power beta times the diameter of K. What is the diameter of K? The diameter of K is the maximal distance between 2 points of K. Like in the circle, the diameter is the maximal distance. Okay? Plus the inverse of mu to the same power beta times the length of K. What is the length? It is the sum of the lengths of all edges. Okay? If this quantity is less than this sort of magic number epsilon, then G has no ground state with mass mu, even if there is only one half line. So it is possible to perturb a half line in such a way that the ground state is lost. Okay, it depends on the structure, on the relationship between epsilon, the length, and the diameter. So you see, for example, that if mu is very large, whatever is the diameter, the first term will immediately exceed epsilon. So if mu is very large, this theorem does not tell anything. Okay? It could be a ground state, and in general, if mu is very large, there is a ground state. But also, if mu is very small, then again, if mu is very small, the second term can exceed epsilon. So in general, you will find a ground state. But it can be if the diameter and the length of the compact core of the graph are suitably chosen, then it can be a region of masses in which there is no ground state. And the philosophy is the following. In order to destroy, so you start from the half line, you have a very strong ground state, you attach something here, and you want to destroy the existence of the ground state. In order to do that, you must have a small diameter and a large length. What does it mean, small diameter and a large length? It means that there are many edges, so the sum of the length must be large, but it must be short, or very knotty, very intricate. So all points are quite close. Now the simplest example we thought of was this guy here, the N4. Remember that for the 3-4, topological construction, you find that you always have a ground state. But if the number of forks of pendants increases, the situation can change. So if the length of any pendant here is the same and is equal to L, then the diameter of this set is equal to 2 times L. Okay, because the distance, the maximal distance is between two vertices, L plus L. Okay. But at the same time, the length is N, where N is the number of pendants, times L. So now one can try to match these two numbers, N and L, to make the theorem effective. And it is very simple, because you fix mu, and then you want L to be small and N to be large. So, for example, fix the number of, once fixed the number of the pendants, decide that L is equal to N to minus 1/2. So, what happens here? And so here we have mu to the beta here the diameter is 12 plus 1 mu to the beta and L. Now if L is n to the minus 1/2, here you have n to the minus 1/2, and here n to the 1/2, the square root of n. Of course, this must be less than epsilon. Of course, if n is sufficiently large, then this inequality is satisfied. So this is quite. This is not a proof of the same kind of the previous ones. So cut, paste, rearrange, so the sort of funny proofs that can be combined. This is really a quite heavy analytical proof of pages of this. So this is just to say that there are different techniques to conversion to this sort of problem, different difficulties. This is a much more difficult problem than the problem of the previous one. Okay. Even though there are always star graphs, this is a star graph with 3 infinite and 1 finite edge, and this is star graph with 1 infinite and many. Okay. And this is all for what concerns the so-called subcritical case, which is the following. Okay. This is basically the almost complete collections of results, not of proofs, not of techniques. Okay? The only technicality I introduced are the arrangement, which is probably the most important, but there are others. But here you have quite a collection of results and many problems with open. For example, this guy here. If you have a line, then on the line you have 2 pendants. What happens in this case? Fixed point. Does a ground state exist or not? We know that for large width there exists a ground state. We don't know whether when exists a ground state there is a symmetry breaking or not. Probably there is. There is not in For example, this is a simple example in which we are not able to say too much. So tomorrow we will give some overview to this problem, the existence of minimizer in the case E equal to 6. Which has also physical interpretation. And I just warn you that this is much more delicate than what we saw. Okay, for today, I'm done.
Any question for Riccardo? Okay, now we